Now we're going to look at some of the UML notation that we use to represent the classes and the relationships of the classes, both the static relationships and dynamic relationships. The analysis class diagram shows the static relationships among the classes of objects. You can recognize the classes. They're the three-part boxes, where the first part of the box has the name of the class in boldface type and centered in the box, and then the second part of the box has the list of attributes, and the third part of the box has the signatures of the operations. You can go to various levels of detail to describe these, and some people just put the names of the operations, and other people put the full signatures of the operations. Some people put the complete data type representation in the attribute list. Other people just name the attributes. I think you could start out with just names of things and then add more detail as you learn more about the attributes and the operations. Notice that the notation, the sort of the syntax of the attributes and the operations as well is more, well, it's not like C++ or Java or C#. The syntax is more like Ada, Pascal or Ada. Actually, is derived from the programming language Ada way back when they invented UML. They were highly influenced by the Ada programming language. Unfortunately, I mean, because Ada seemingly has gone away by now, but that's still stuck in the syntax of the UML. By the way, Ada is sort of the default inner syntax. You can use whatever inner syntax you want on your project, as long as your tool set will be able to support. I mean, the whole idea of having a fixed syntax for variable declarations and operation signatures is that a tool ought to be able to take this diagram and automatically generate code from it. And so if you're using a tool that does that, then you are forced to use some predefined syntax for the attributes and operations. Although the tool could support various languages if you look at your tool. And so you may not be forced to use this Ada syntax. You could use Java syntax for some tools, I suppose. The three-part boxes are the classes. The lines connecting the classes are called associations. We saw this when we looked at entity modeling, entity diagram modeling, right? A video class describes video copy. Now, it's actually these relationships, these association relationships, actually represent relationships between object instances of the classes. So an object instance of the class video will describe an object instance of the video copy class. Right? So the video copy will not contain information such as the title and like the running time, the length of the video. Why? Because all video copies of that same video presentation will all have the same title. So what we do is we factor that information out, put it in this object called video. And so we have the association between a video object. So one video object may describe multiple video copy objects. So the class diagram, in order to show this, what is called multiplicity, right, one video object will describe many video copy objects. To describe that multiplicity in the class diagram, we use these symbols. Okay, so we see a 1 here and a star here. The 1 multiplicity means all of these video copies will be described by only one video object, but that one video object may describe multiple video copy objects. So rather than showing a class diagram, multiple class instance diagram, or excuse me, an instance diagram like this, this one class diagram sort of represents many instance diagrams like this one. Video copy could be rented by a customer, right? So each one of these video copies could be rented by a customer. Now, how many customers can rent a video copy? Just one. A customer can rent how many video copies? Well, I've got a star up there, so I could actually have that same customer linked to many different copies. We have an association between video and customer. That's reserved. Right? So a customer could reserve a video. How many customers can reserve the same video? Any number of them. How many videos can a customer reserve? Any number. That's what the star means. This dashed line to this association means that in addition to the information, the fact that the video copy is rented by a customer, there's also some additional information that is stored on that association, that link, and that is the due date. The dynamics can be, we have different models in UML. There's only one, seems to be one model for describing the static relationships, but there are lots of different notations for describing the dynamics. And it's a choice, sort of a preference choice mainly, because you could use different notations, and they'd all work. You probably wouldn't want to use all of them. You probably want to choose which notation suits your project the best. But what we're doing when we're analyzing the dynamics, we're running through the scenarios like we did with the example we did in class. And then remember, at the requirements time, the scenarios were in terms of the black box. The use cases, for example, represent the sequence of messages to the system. We indicate what the system does, but we didn't indicate anything about how it worked. At analysis time, we know what's inside the system, and so now we're exploring how those objects collaborate. Okay. Some dynamic models: activity diagram, sequence diagram, and state transition diagram. We've seen some of these before. And here's the activity diagram. So here's our little tree problem that we did in class, written out as an activity diagram. Remember the bars here, these bold bars, these are synchronization bars, for can join. So the beginning of the whole activity starts here, and the first thing we do is we, in some order, and it doesn't really matter, it's all, say, asynchronous, we need to initialize the pi, we need to get the initial tree, and we have to initialize the counter. Once we've done all of those things, then we put the initial tree onto the pile, and then we come down here and say, is the pile empty? Right? If it is, we display the current value of the counter. If it's not, we get a tree from the pile, and then we got this decision. If that tree has subtrees, you split it and put the trees back on the pile. If it does not have subtrees, we discard that tree, and we increment the node counter, and this happens in either order. And then we go back up here and keep looping around until the pile is empty, and we finally display the counter on the standard output device. So that's a sort of a flow graph or an activity diagram of what we did in that little act out thing. Sequence diagrams most commonly used for describing the dynamic behavior, because you can get down to a lower level of abstraction. In the sequence diagram, each of the objects is represented as an object instance box on the top of the diagram. Okay, much in the same way that the activity diagram has these what are called partitions or swim lanes. So each of the classes of objects, actually these are not classes, these are object instances. So I have an instance of customer, have an instance of video copy 1, and an instance of video copy 2. And the messages, there's the actor from outside the system. Right? So messages are represented as arrows. So here's a message from the actor to the system, and it's actually received by the customer object inside the system. The real customer says, I want to rent video copy 2. The next thing that happens, now the reason it's called a sequence diagram, it's a sequence of messages, and the order is a top-down sequence. So the next thing that happens is the customer asks himself, customer object sends the message to itself, am I in good standing, basically. And so we see another sort of focus of control box coming off here, nested inside that. So you know, we're still executing the rent operation, but now that same object is actually, in addition, executing the is in good standing operation. Now, in order to perform that, it has to send a message to every video copy that customer is currently linked to, and says, are you overdue? Because the video copy apparently has the ability to know whether it's due or not. It knows what the due date is. So in this case, the result is false. And let's suppose that every video copy returns false. Right? So then the result from is in good standing will be true. the customer is in good standing. And then the customer says, all right, now I want to rent the video copy VC2. Well, first of all, it has to ask, is VC2 available? Because there may be some state-related things about the VC2 that make it not available. In this case, VC2 is not being rented by anybody else. It's available for rental, and so it returns true. And then the customer says to VC2, rent, and passes a reference to himself, C1, as an argument, and the video copy VC2 will set up the link between that customer C1 and itself VC2, and we return. Notice the returns are in dashed arrows. The message sends, if you will, are in solid arrows. You could also do a state transition diagram. Here are the three states of a video copy. When it is initialized and constructed, when that object gets constructed the first time, it has the state in store. And then when the video copy is checked out, it goes into the checked out state, and then it gets checked in, checked out, checked in, checked out, checked in. And eventually, after the video copy has been checked out, say 200 times, I don't know, whatever the rule was in the video store, in this case it's 200 times, then it goes into the for sale state. So the video store will say, well, we've rented this thing enough, let me just sell this thing cheap to whoever. So video store pays like $15 for the video copy, rents it out $4 a time for 200 times, and then it says, well, let me sell this thing, and I'll sell it for like $12.